Good evening, friends. Welcome to Eastern Academy. We are into understanding all about ARM microprocessor and microcontrollers. Okay, that's not our session. We are trying to understand about very thorough understanding about ARM microprocessor and microcontrollers. And the last session we discussed about why ARM. First of all they did was they've increased the 8-bit to 32-bit. First. Second was they have reduced the instructions, okay, by making it as a RISC. That means that they did everything in the hardware rather than the micro programming, which increased. Third one, they did a pipelining. So they could make the access very fast. That means that if they fetch 132-bit, okay, that's enough. That's on one cycle, they execute one instruction by doing a pipelining, 3 activity. That is one unit will fetch, other unit will do the decoding, and third unit will be doing the execution. All the 3 will be happening parallelly. So it's a pipelining. That's called, if something is happening on parallelly, it's called pipelining. Okay, so, and fourth one was they made all the instruction within the single access. So I can access 32-bit, the processor. All the instructions are 32-bit. That means that one access is enough. So like that, they made so many things and they did everything on a very less transistor. So the power also less. So exactly for the embedded systems, when I like to have a more power with less cost and less size, think of it, more power, less cost, and small size. So all the things are matters. And what happened was this was perfectly fit for battery operated devices. That's a perfection. That's a beauty of ARM. ARM era was started with battery operated devices. That's it. So it consumes low power, and because of that, the long life of the battery. But I don't say today. Today they use the ARM processor even in supercomputers. Okay, so it's correct. Of course, the power is still less compared to Intel processors because of the way in which they architected this. That's fine. But they said fine because of the silicon. They said that instead of making one processor, let me make 4 processors. Okay, and we have seen that how they have made a processors inside a single silicon. Okay, so we'll just have a look at them. These are all information. First, let us go into the information. Then we will get into the this one. Okay, so we'll get into the next one. So today we are going to discuss about ARM microprocessor hardware. Please understand, we are not going to discuss about microcontrollers. First, we finished hardware today. Tomorrow, next class, we will have about ARM microprocessor software architecture. Once we understand about what is the ARM microprocessor software, that's enough. Then, see, the microcontroller we already discussed. We know everything. The only thing is I have to connect them, all of them. There's nothing great in it. We will discuss about coming days. You'll be very surprised. Most of the things that we discuss in the embedded system programming. The same thing will be coming here. Now, this is what we discussed. First, ARM. See here, there's a very tricky one you should see here. This is called ARM v1. The small v is it's called ARM version 1. This was the first processor released by ARM. 26-bit address. 20 6-bit address, 0 to 25. And then they have a 32-bit data. That's correct. That is the first ARM processor released in the market. Understood? We have seen this in last class. And here they have a barrel shifter to do the multiplication. See that? Just see this picture and see the next picture, ARM V2. Version 2. They've done nothing much. Everything is same. 26-bit address and 32-bit data, and everything is same. But what they have done was a small change is the multiplier. Okay, they added multiplier. Okay, and that you have to do it through the software only. That's fine. So this is what only thing was added in the ARM V2. Now they have moved to ARM V3. Sorry. Oh, sorry. See the ARM V3. There's a first time they've increased to the 32-bit address. That's a major advantage now. Understood? 32-bit address has been included, and big. Is it? I have not noticed. Sorry, thanks. Somebody you are noticing. ARM V1. Oh, the incrementer. Okay. They increment by 4 also. They instead of incrementing by 1, they increment by 4 also. That's correct. Yeah, that's nice. Somebody has watched. So nice. Good. Now, I'm becoming old. You're right. So this one is on the 32-bit. I have about here is the first time they introduced 32 address lines. Okay. That is a major advantage of the V3. But from here, there's a confusion started. That's a trick. See that. What they have done next. That's a beauty. You slowly will understand. Go through that. But today you can learn it and forget it. See here. Please understand here. I called ARM V3 here. Am I right? You see here, ARM 3. But ARM 3 is having a ARM 2 core, but they have a cache memory. The tag cam is for cache. And the co-processor control. That means that I can have one more processor, like a math processor or floating point processor. The problem is the silicon those days was too small. They could not keep anything on it. So what happened? They kept these things outside. Let's say, if you want to have a mathematical operations, add a co-processor. Why they call see, they do not call that as a controller. They call as a co-processor because that will be an instruction here. That instruction will go there and do the thing. So it will be like a part of your ARM processor. So now understand here, you have an ARM core, but see that you have a cache memory is added. This is ARM 3 there's a thing here. ARM V3 is called architecture. This is called architecture. This is called processor. They added this. Also, please understand one thing. They started using the word called core. See here, they started using the word called core. Core is a typical architecture. That's what I have shown here is a core. Please understand. Now, core does ALU. Core has a ALU, a registers and the control unit. Okay, that's in the core. Core does not have a cache memory. Core does not have this one. Co-processor controls. That thing. So many other things what you're going to add in future. Those things are not part of the core. Please understand. So core is a simple unit. So today we'll discuss about hardware. Tomorrow I told you that we will start doing the software. That will be more interesting than this. You all, I know that you all are very interested in the software, but unfortunately, I have a mechanism. I cannot just jump into the software. I have to tell you certain basics. Okay. I want to give you the overall picture, a base. But as I told you, after today, you can forget this. This is not going to affect you anywhere. But this is the information. All these things are information, not me. Nothing is logical here. All information. Now you see here, let us see now. This one, when they made it to the chip, silicon, you have a small view about how it was in silicon. That's the most important. See here, your core was here in the silicon. That is only 25%. But your cache is occupying about 50%. Am I right? Okay. It's actually a cache memory of 4 kilobyte. 4 kilobyte. That itself occupied how much space in those days? Think of it. In a small chip. And all the tag cam also, we'll explain about. Today, if time comes, I'll explain about the cache also. You will know that what is a tag or not. Okay. Content access management. That means that they find out where the content is. That's the way. They are also indirectly memory only. Content access memory. Tag memories. So you see that this is, no. You have to understand where you are today. Also, you have to, don't get confused with the ARM. ARM have a ARM 3, uses ARM 2 core. Okay, that's a problem. Now let us see here what they have done. Afterwards, slowly they came to ARM 4, 5. That is not important because we are not going to talk about history. I'll show a little bit later, but this is the one you have to understand very thoroughly. This is what ultimate. Today, all your mobile phones, all your embedded Linux systems, okay, or your latest Chromebooks, so many things, they started using only A series. We will discuss about what is A series today also. And that has, see that, 64-bit and 32-bit CPUs, both 64 and 32. And they also have a 32-bit address, 40-bit address, and 44-bit address. Understand? 44-bit address is there in A series. But whereas R series is a real time. Please understand, this is the processor exactly meant for RTOS. R4, R5, and R7. Okay, they are too good for real-time processing. Okay, that means that we'll discuss what exactly they do it on real-time processing. We'll coming the slides, we'll see that. You know that this is what M0 they started. Actually, they made the M0 plus. People today mostly use M0 plus. And this M0 and M0 plus are equivalent to like any 8-bit controller. Very small space, very cheap, very, very cheap, and very low power consumption. They will outbeat. Actually, that M0 is a competitor to all the 8-bit processors. Okay. Somehow, these people Arduino people have taken by wrongly Atmel processor. They have taken a M0. Things would have been wonderful for ARM. But somehow things have happened. The one which is popular. See, there were two things happen in the industry. There were two things happen. In 1970s, 75, 76, there were two companies who were making microprocessors very majorly. Unfortunately, Texas was doing only with military application. Texas microprocessor were used only for military applications. And 6502 was used for smaller application. There were two powerful people who were fighting. One is Intel, one is Motorola. Actually, to be frank, Motorola processor was too good. I worked on it. It was too good compared to Intel. But the mistake was IBM have chosen Intel. This is because Intel has the capability to convince them. Also, they had a lot of peripheral chips, which are used that 8255, 8253, 8259. That is we call ecosystem. Because of that, they use same way happened here. Just before ARM getting slightly popular, the M0 and all, that Arduino people, that college students have used at Mega processor. Okay, if they used ARM processor, things would have been much, much better. Like that, industry does sometimes small mistakes, which slowly correction. Now I think in the short time, ARM will replace an Arduino. I hope so. So whether it's right or wrong, Arduino become popular. Okay, don't mistake me. It become popular. Then you see here, ARM 7. I've written ARM 7, but actually it has uses ARM v3. Please understand. This did not use ARM v7. ARM 7 and ARM 9 uses ARM v3 cores. And I think this is v5. But here, Cortex M0 onwards, all the M series, which is microcontroller, which uses very low performance. I forgot to tell you one important thing. That's a thing here. When you go to the previous one, this is what here. You see here, M0 we discussed. And M3 is a very popular. Once about 10 years back, NXP's processor. That time ST was not very popular. NXP was very popular, and M3 was very popular. When suddenly M4 started coming and ST came in and captured the big market. But M7 is a very high performance. See that it has a DSP core. Okay, and first time this is having a built-in cache. This M0, M3, M4 do not have a cache memory inside the processor, whereas this M7. So you cannot say in future microcontroller M series application do not have a cache. No. It is true up to M4. When there's a M7 came, they put a cache memory, and automatically when you put a cache memory, things will become performance will increase. We will discuss today also how the cache memory will increase the performance. That's fine, little. And this is what is started. Okay, slowly, and it's gone beyond that. Okay, R series, R5, R4, R5, and today R7. Actually, in my previous company, I worked was R5. We do the processor. We had multiple R5 inside. See, they had a beautiful advantage that you may not know that. Why they call real time the things are all. The two R5 can run in parallel. One will be master, one will be slave. If suddenly one R5 goes bad, the other R5 will continue from the place where it is left. Understand? This is a very, very nice feature. Fault tolerance. These all, there's so many things are built into the thing is, even though it started as a very small, less complex processor, it is becoming more complex. We'll discuss now. We are going to see that. But this is only for information. This, you are not going to work on it right now, and you are not going to use it now. This is only for today. Only for today, I'm passing this information to you because I want you to know that what it is. Otherwise, it will be very difficult for me to proceed to the software. And this is the basic hardware platform. Now you see here ARM V1, ARM 1, ARM V2. See here, ARM 2 and ARM 3. Whereas ARM V3, okay, goes to ARM 6 and ARM 7. This is what your architecture, okay, micro architecture they call, V1, V2. This is the processor. Don't get confused. The Cortex, see that. When you go to ARM V7 onwards, they start getting into the Cortex. Of course, there's a small correction here. In Cortex M0, they use V6. That's fine. They just not. So today we don't use them. Today these are all the things. ARM 2, ARM 3, ARM 6, ARM 7, all of them are gone. Don't worry about that. Okay. Today, we are using only Cortex. Enough. And M series. And not much M3. We use M4. And maybe shortly, we will get into M7 fully. Okay. Or we don't use R4. We use R5 like that. So please understand this. This V1, V2, V3 are core. Now up to V9 has come. V8 and V9 has come. Okay. This is what the core, understood? They call CPU, central processing unit. Whereas Cortex M0 Plus is this. They add so many things. Your data watch point, breakpoint, micro trace buffer, MTB, debug access port. We'll discuss all these things, what this. And AHP light interface, low latency IO interface. That means that when an interrupt comes or anything, it will be very fast. And memory protection unit and nested vector interrupt control. Wake up, these are all part of hardware of M0 Plus. So you have all these facilities are there. Understood? This is what Cortex M0. Then you go to Cortex M3. Okay. They have some more provisions here. Okay, they have a core interface and they have a SRAM peripheral interface separately, debug access point and serial wire viewer and memory protection unit. Yeah, I'll explain to you that. I'll explain to you that. That's very nice. That I'll explain all the bus matrix unit, debug access point, and serial wire viewer, memory protection unit, wake up interview. This one interrupt controller and nested vector interrupt controller. Okay, and all these things are ETM. I'll explain all this. All these things. It's called trace monitor. What is a trace monitor? All those things. Every block. First we will go through that. Then I'll try to explain as many blocks as possible. And it will be very useful today to understand what are these things. And as I told you that, learn it and forget it. I don't want you to keep them unless otherwise you get into the hardware design or deep architectural design. Right now, you are going to develop a software above ARM. Okay. For that, these informations are not much useful. Then next, you see the car M4. Okay. They have much more facilities here. Okay. So they have a floating point unit. They have a DSP, all those things, extra added. That's what they keep on adding your blocks. And they call it the thing. But the CPU is same. They keep the same Cortex CPU. That is, you see here, they have given here everything. That's the reason I told you, no, I cannot, this is actually a cut and paste, which you can go and see the thing. See here, Cortex M7 has a problem. Okay. You have a, see here, cache memory, 64 KB. Okay. There's something called write through, WT means write through or write back. I'll tell you what are them. What is a write back and write through? I'll explain all the terminologies. Don't forget it. I'll go slide by slide later. I'll explain this one. See, this guy also having a TCM. Okay, tightly coupled memory. We'll discuss about that. What is tightly coupled memory? Okay. And APB, AHP, Dcache, iCache. You have so many terminologies. AHP slave, AXI master. Almost what they have done was, what is there in the R processor, they brought into the what? Into the M7. So that means that what they are trying to do is, they're trying to bring the power of R series into M series. That's what it means. Understood? These are all the terminologies, all nothing. AHP, APB, AXI, TCM, these are all small. Once you know that, you will know that FPU is called FPU, floating point unit. You see that? Single and double precision. That is what you say float and double. Those things are done here. Understood? This MPU. MPU is called Memory Protection Unit. Okay, that's what it does. So we will discuss all of them. So this is what Cortex M0 plus. I don't discuss about M0 is gone. M0 plus, M3, M4, and M7. Okay. Now, let us go next. This is what the matrix gives you, the general performance of M0 to M7. Okay. Drystone, this all, how many MIPS per megahertz? So see here, how many MIPS per megahertz? It's called Drystone MIPS. That means that the method they calculate how many million instructions per second is called DMIPS. Actually, it's a MIPS per second. Okay. They have a, since it's a Drystone, there's a standard. There's a standard how they calculate. I told you that day, because when you do a RISC processor, the problem is that they do a lot of instructions faster, but the output may not be as effective as a complex instruction. That's why they come out with a new mechanism called Drystone MIPS. And what is the area of the die? How much power it takes? See, microwatt per megahertz. Microwatt. Okay, if they say that M4, you take 8 microwatt megahertz. That means that if you have a 100 megahertz, then it takes 100 microwatts. Okay, what is the I don't know dynamic power in the area? It's fine. This is the area of the your die in so many mm square. Okay. So this is a general matrix M0 to M7. Nothing has changed. Not much. You see the performance, nothing has changed. Only thing is the speed is increased. That means that when I could operate this at 10 megahertz, 100 megahertz, I may operate this 200 megahertz. And also by MIPS has increased by twice. See that 1.25, 2.14. So this is all very important when you do the processing or trying to select the right processor. Now, this is what the Cortex M series memory map. This is a memory map. This we know that 32-bit 0002 FFF. And this is all the Cortex, whether it's a M0 or M7. This memory map is common for all the Cortex series. Understood? That's the reason they make it as a Cortex memory map. I forgot to write the heading. It's a Cortex memory map. Where you see here, entire 32-bit, they have it here. 0 to 2000. How much memory this is? Can you tell me now? Quite quick, fast. 0002 200. How much? So fast. So quick. By the time, that's why I've told you now. These are all have to come so fast. So if somebody asks you that what is the code region, quick, 1 second. 1 MB? Oh God, it's too low. How many zeros? It's about 7 zeros. It's about 7 zeros here. 70 is how much? $70 is how much? 1 GB. Is it correct? How did you calculate 1 GB? They all see the problem. That's what finally where we land up. That is what the problem. Everybody wanted to learn ARM, but we do not put our mind on this. You see here, 0, 0, 0, 0, 0, 0, 0, 0. From 2, 0, 0, 0, 0, 0. I ask, how much is this? If you cannot give an answer within 10 seconds, you need to go back home and practice this. This is very, very important. These are things very, very important for the ARM. when you come up to the arm level of discussion, you say that you have a problem in the basic binary addressing. Nobody will like. If you have come at the interview, if you have not told this in the interview, I will not be happy. I will write the point to management. The person, the candidate does not even understand about addressing. What is the capacity of this? Yeah, at last I got the answer. I know it's so easy, man. Forget it. This one is changing. This is not changing. You have 7 to 4, 28. 2 power 28 is how much? 2 power 8 is 256. 2 power 20 is how much? Meg. 256 meg. This is for 1. Now I have 2 zeros into 2. It's equal to 512 meg. That's why 512 meg is the correct answer. 512 meg. Now you see here, in this memory map, totally FF from 0000. So the total memory capacity is 4G. The total memory capacity is 4G. For the flash, okay, they have how much? 512 MB. Then they have a .512 meg. You should be able to calculate this. If you know how to calculate this, you have done. These are all the required as a firmware engineer. I don't expect you to know great things, but I have to expect you to know that total calculation. Now you see here the next one, SRAM. SRAM is having how much? 400. 4 minus 2 is 2. Once again, 512 meg. Then what is the other one? Peripheral. How much? 0x6000. This is a static address of other region. Please, the peripheral base address is this. I told you that day how to calculate the base address. How to calculate the base address. This is the base address of peripheral. That means that all the peripheral devices, when you are going to discuss about microcontrollers, you will know that how important the base address is. Every address will start from 4000. Now, the 6 is where which starts, RAM region, RAM. Up to out to 0x, sorry, remove 0x, not A00. Now, how much is capacity? Now, tell me what is the RAM size. Can you tell me what is the RAM size? One G. Then what is the off-chip peripherals? How much? Off-chip peripherals. How much? Anybody? Anybody? Quick. We are late. 1G. Perfect. Now we are getting slowly good. What is this? This one? System components and debug. How much? No, so far, no correct answer. 512, correct. It's a 512. So if you add everything, this is half G. This is half G. This is half G. This is 1G. 1G of G. So if you add all of them, you get 4 gig. You have to have a very good clarity on this. Please understand. This is very important. So do you understand this? How I have calculated? So you have to do it very fast. So this memory map is another important thing, because see, the problem is previously all your processors are 16-bit memory, and this is the 32-bit address. Think of it when you go to 40-bit and all, how you will do that. So better learn it very clearly. This. Okay, that's fine now. Let us go to the next slide. See here, this is what another one information which I have to tell you the thing. You see here, your process, even except M0, even a M0 plus itself has this thing, Cortex M series. I'm not worried about too much right now, your A series or R series. First, we will try to go. I'll discuss about A today, but we slowly I'll converge it to M series. Once we understand M series, then we can go to the next one. You see here they have a OS, means they call about RTOS, not your, what do you call it? Your Linux or Windows or anything. This is actually RTOS, because they cannot run in the MCPU. You cannot run Linux, please. Okay. Now you see here, task A, see that they have made these things as a red color. They have something called MPU. Understood? They have got something called MPU, Memory Protection Unit. Now, it's called Memory Protection Unit. I'm not generally, yeah, it's the same. But the only thing is, see here, please understand, you are right. Okay, one thing you understand here. I am not discuss about microcontroller now. Please, I am discussing about microprocessor. I will discuss about this later. They have given peripheral region. That means that whether it's a LPC 1378 or STM32 processors, if you do the address, the peripheral will start from 4000. That is correct. Okay. But what peripheral they use, what is the address, that depends on the company. ST Micro will be different and NXP will be different. Please don't get confused there. They said peripheral. Understood. They never specify what peripheral. This is what I was trying to tell you, that don't get confused between microprocessor and microcontroller. This is only microprocessor. When we discuss about microcontroller, maybe after a week, next week we'll discuss about software, because we should know about all the registers and other things. Software model. There's something called software model is there from that all the people follow. Better we understand that. Once again, I'm giving you that these are all only a starting point. I give you as much as possible, and I'm enabling you to discuss with me the same thing. But there were tons and tons of information on the net. Try to find out, read it. If you don't understand, ask me. I will help you out this. Don't you? This I'm trying to ignite you to get into the ARM series. I want you to do the ARM slowly. Now, previously, we have understood about all the microcontroller, memory map, peripherals, everything, controllers, everything. Now, we are going to do it to the ARM. That's a trick of it. Now, you see here, There is a difference between MMU. There is you know that all the Linux platforms or Windows platform, they have something called MMU. Here they call MPU. MPU is not MMU. It does not do MMU functions. I'll discuss when we are discussing about MMU. What are the functions? This guy does not control your virtual memory or physical memory. Anything. What this guy do it? You can specify that each task as a mode. That when we are discussing about software, I'll tell you that your ARM processor can run on multiple modes. That's called supervisory mode, user mode, interrupt mode. It can run on so many modes. You can say that on the user mode, they should not touch the kernel because that software should not come and spoil you. Am I right? That is what they say here. See here, improves systems reliability. That is very important. Your embedded system, somebody should not get in and spoil your system because of using software. Okay, previously it was hardware. You know, there's one more problem we are facing nowadays. You should understand that. It is because of your because of your IoT. Because of IoT, you are exposing your product. I'll 1 minute. I'll try to explain this because sometimes we don't understand why they are making it so complex. Why they are making it so complex? That has to be understood by you. The trick here is when I do it only hardware. When I do it only hardware, then somebody have to have a physical access. You'll be surprised that why this ARM keeping so many complex things. Because it's a very unfortunately, the ARM entry along with that was your IoT. Now the trick here is when they have a physical access itself, nobody can do anything. Otherwise, they have to come to your house, open the box, and change the wire, everything. Otherwise, your things will work fine. Now, when I make it as a software only, that time also, there's only one problem. The thing is that when you try to upgrade your software or do something, some mechanism using your SD card or something, by mistake, you can access something. That's why they need it. But when you connect your embedded system to the internet, so how a virus came to your PCs, okay, how your mobile phones are getting affected by spams and illegal access, same thing, you are going to expose your embedded system. Understood? That's why they have all these provisions such a way that even an illegal software through the internet, through net, IoT is nothing but internet of embedded systems. This thing is nothing but embedded systems. That means that your embedded systems are vulnerable to all the network attack, all the virus attacks. When the PC attacks, when the PC is attacked, you lose your information. But when the embedded system attack, I can open your house door. I can on your cameras. I can do anything. What is happening on your things can be seen by me. That's the reason they have all the provisions for these embedded systems. Security. You will be seeing not only this, coming days, you will be seeing the next revisions, more and more security. Understood? So see here what they do. Configurable region address. That means that the address you should not access. You should not access more than size. Memory attribute. You can only read, not write. Access permissions. All these things are configurable. Okay. These are all provisions available on your Cortex processor. There were too much of options, man, software, hardware. But software is lagging too much. It will take another so many years to catch the hardware, the software. Now let us come. Let's go to the next one. So you understand now. That means that I can configure that I have multiple tasks. I can say that certain tasks only access certain memories. That means that this task B can access data for B and IO. He cannot access this ones, task A ones or the kernel. That's not possible by the task B. And task C can access only data for task C and IO, but he cannot access. But task A can access them. Understood? And you see here, this one is the OS kernel. That guy is having a different color. That guy can access only data in OS kernel. That tomorrow when we are discussing about software, I will tell you all the modes. Not tomorrow, so next session. Always everything tomorrow. See here, this is what another Cortex M. This is a very, very advantageous. See here, they have a interrupts. Okay, nested vector interrupt. This has so many interrupts it takes. But the thing is that if I have two interrupts coming together, if one interrupt is waiting, you do the push when the interrupt comes. This guy is doing so intelligently. Okay. It's called optimization. Tail chain is one of the optimization. That means that I will solve the next interrupt, then I will do pop. You understand now? I do not push and pop. This is what we do it when there's an interrupt comes. When there's an interrupt comes, I go to the ISR1. Come back. Then I go to the ISR2. Come back. Every time we do push and pop in the stack. Whatever I use here, I do push and pop the stack. So I have to push, pop, push, pop. Now, this guy is having a nested interrupt. They had a superb idea of not to waste this time. When there's a one interrupt comes, before you complete the interrupt, other interrupters come. The first interrupt, second interrupt. Now what that guy will do, he will not do the wasting the time. He will do this one, then he will finish this. Interrupt one will complete, then go back, interrupt two, he will complete, come back. This we will discuss when you are there. I'm just giving you the idea because this is having the hardware feature here. We will see that. And also, this is a very, very beautiful thing. The interrupt table can be, ISR can be, you can write it on standard C functions. Previously, it has to be in assembly originally. That's why they have written this. That we will see that when we discuss software. Okay. So these are all the features available in the ARM. So I told you that today you can forget it at the end of the session. But at the same time, I have to tell you, I cannot just say that, oh, this is ARM, M0, everything. I will tell you what is inside. Okay. They have compared with the 8051 and Cortex M. See that? Start real handler code and see that? They do so many push and pop. PSW, push PSW. See that? So many things. Then they actually handle the code. So this operation will take about long time. But here nothing. Just this is the beauty of ARM means speed, man. Low power speed. That's it. They made the real money out of it for everybody. And also it has a big priority. Priority is a beautiful one of ARM process. They have 256 levels of priority. You can set which interrupt has to be done first, this has to be second next. This is what I told you. Wake up interrupt controllers. Okay. You see here, when there's an interrupt comes, it will wake up and do the ISR and go to sleep mode. See that? It does the processing. When you are sleeping, okay, sleep mode, come to the ISR, then it exits. Finish. The advantage is in sleep mode, the process consumes very, very low power. Okay. So these are all hardware features. Please understand, this week is a hardware feature. When that guy goes, this guy will give you the interrupt. When he complete, he will put the processor in the sleep mode. This all there's a control, weak controller. Like I think I forgot to explain the ESP classes about watchdog timer. That's like this is like watchdog timer, but it's not. This is called wake up timer. Okay, we normally know watchdog timer. This is a wake up timer, please. And this is what the small comparison, what it does. Sleep mode. I don't know what is SRPG mode. It's a new for me. Let me find out. I'll tell you tomorrow. Okay, OS support. Okay, this is called supervisory control. And MPU. It's nothing but a memory protection unit. Exception handler. And the false status registers. Bitband, I don't know what. I have to find out. Then bus interface. AX, this is too much. AXI, AXP and all. And JPB is a peripheral bus. I'll discuss what is the bus basically. Then cache, which is not there up to M4, it is there here. Okay, then this is TCM, is called tightly coupled memory. It is about 1 MB for this. These are actually, when I was using that on R5 and all, they had it. We used it very quietly, quite good, but now it is available in Cortex M7 itself. They were merging the your R5 and these things. Okay, these are just small comparison of what they do it on M7. So when you go to M7, you have lots of disadvantages. Now you see here, number of interrupts. Here it's about 32, but here about 240. Sorry. 240 levels of interrupts. So many interrupts. And each can have up to 256 levels. And this very low levels. It's about only, these are all 4 levels. These are 256 levels. That means that you can make the priority as you wish. But actually, you'll be very surprised. I told you, in the last product and all, I've used about hundreds of interrupts. 100 interrupts. You will never able to surprise. You'll be surprising how to handle 100 interrupts because every employee will write one ISR. All will be there in the process. Fine. This is a typical thing, and I'll tell you about what is this JTAG and SWB. And this is what generally they do the thing. They have a main bus and they have a bridge and connected to the thing. All the peripherals, everything will be here on the bus. APB, see that? I'll talk about what is AMBA, what is ABB, what is HB, all the terminologies. Most of the terminologies we'll try to discuss today. Okay, that will be the same thing, debug. What is the JTAG? What is SWD? They're all nothing, but you should know that what it is. I say that whether you use it or not, and you may forget it, but still know that what it is. That's correct. Okay. So by the next one, what is that? We'll see that whether it's always I can take a small break. Yeah, I'll take a small break and then come back.